talk about wave behaviors in terms of reflection now in this next topic, 7.2. Now, bouncing ball reflex, right? You can stand apart from your neighbor, your friend, and simply bounce the ball to them, and it will come in at an angle and leave at that same angle on a smooth floor and bounce up to your friend. And waves do the same thing. Um, so actually A in this is reflection. And so waves and particles both reflect. Um, with sound reflection, we know that as echoes. Okay, so we could have a sound wave where you're a person standing out in a valley somewhere, and there's a wall, large cliff over here, and you yell something out like moon. Remember that story at all of Little Bear and the moon? And the wave will travel to the wall, bounce off of it, and come back. So if you yelled something like moon, you'd hear moon back after some time delay. Well, of course, we know now because the speed of sound is 330 meters per second approximately. If we timed how much it took for it to go there and back, say that that time that it took was zero point 0.1 seconds, okay, to go there and back, um, then we could find the distance that the wave traveled. So we could find this right here. So we would know 330 meters per second would equal delta S over zero point 0.1 seconds. So delta S would be 330 times 0.1 or 33 meters. And that's the distance that the wave traveled, okay? But we also have the distance to the cliff from the person. The distance to the person, or from the person to cliff, would be half that, wouldn't it? If it took that time was to go there and back. So it would be half of 33 meters. 16.5 meters. Now this is a common technique used by um, blind people to actually move around and know how far away something is by a series of clicks and the echo return. Their ears are sensitive to pick up, and trained really to be pick up that delay and know. And of course, bats use it in like sonar to detect how far away a bug is, and zoom in on it, capture it, and eat it, things like that. Okay, so that's a sound reflection as an echo. The light reflects when we look in a mirror, and our image looks like it's coming from behind the mirror when in fact it's light bouncing off the mirror going into our eyes. And that terms of reflection, well, and the same in echo too, or is off a smooth surface. It's called the law of reflection. And the law of reflection, we have a line in that, and we call this line the normal line, okay? And if we look at the light as a ray of light coming in, like this, the light's going to bounce off at an equal angle off like that. And we label these angles. And it's the angle to the normal, which we call theta I, and the angle to that comes off is theta R. And the law of reflection simply states that theta I equals theta R, okay? That the angle of I being incidence is equal to the angle of reflection. So it's really quite simple. But of course, most surfaces are not smooth. Some are quite smooth, like the desk in front of you, and you would see some reflection off of it. But some is optically rough, like a piece of paper. It looks smooth, but if you look at it on a microscopic level, you can see that it is actually quite rough. It's not very smooth. Tile, like in the bathroom, is like semi-smooth optically, and you can sort of see your reflection, or the reflection off of the tile somewhat. Um, the mirror is much more optically smooth. So, but in those surfaces, like let's take an irregular surface, like something like this, okay, on the optical level. Why does it not reflect the light to look like a mirror? So, in a mirror, first off, you could think of like a person standing there, right? Here's their eyeball. Let's put a hat on them. Okay, just real quick for a hat. And so as they stand there and they look at the mirror, the light from the hat comes in, let's do that in red, comes in like that and then bounces back to the eye. And there's the normal line, okay? So the eye, of course, the eye sees things as traveling in straight lines. It doesn't, it somewhat interprets it that there's a mirror there and it knows it's not behind it. But the image will look like it's coming from the eye at equal distance back. So we'll get the hat will appear to be, as everything else will, appear to be behind the mirror there. And that's due to the law of reflection. The same thing happens, law of reflection holds on non-smooth surfaces, but the angles go off at a whole bunch of different. So let's say we had light coming in like this. Okay, here's a beam of light. Here's another beam of light. And here's another beam of light there. Okay? Now each of those have tangent lines to them, so that are tangent to the surface. Like there's one, and there's one. At 90 degrees to those tangent lines is the normal. Okay? And we can see that the reflected blue line in each case, in this case, because here would be the angle of incidence, and it would come back at us like that, so that would be the angle of reflection. And over here, the angle of incidence is that, and then the angle of reflection is like that. And over here we have our angle of incidence, and our angle of reflection is like that. And so you can see that these angles of reflection, one of them is going off like this direction, another's going off in that direction, and another one's going off in that direction. So there's no consistency to which way the reflection is, and therefore there's no image that's going to appear to us as coming directly to our eye off of it because it's all in different directions. Okay. All right, so that is reflection and the law of reflection. You can also get interference. So this will be like B part. And we'll do some demos with this with Slinkies in class, and then we'll look at that. So two particles like tennis balls or electrons or protons, they can't occupy the same space at the same time. You can't take one tennis ball and put it exactly where another tennis ball is. But waves don't have that constraint. We saw that the other day when we looked at the Slinky traveling across. We looked at it real briefly, and I didn't really mention much about it, but it appeared that one wave just traveled through from one side, one person generating it, through the other wave that the other person generated. And we'll look at specifically how that works. The waves can occupy the same place at the same time, and what they do there is they undergo something that's called the superposition principle. And so if you have one wave energy that causes a displacement in the medium, and another wave energy that causes a displacement in the medium, and if they meet up at the same place at the same time, their displacements in the medium just add together. Okay? So the amplitudes, the displacements, amplitudes of multiple waves just add together. So it's nice because we've had these simple formulas, right? We've had the one that we're used to, velocity is delta S over delta T, and that in terms of waves, it's velocity is lambda, the wavelength times the frequency, and then we had the law of reflection, which is angle of incidence equals angle of reflection, and here we have the total displacement caused as a wave goes by, and we're just calling it D here, which is D1 plus D2 plus how many ever waves are going over that moment at that instant in time. We just add them together. So what does this look like? Well, there's two different situations. It could be constructive interference or destructive. Okay. Let's look first at wave pulses. So in destructive interference, the two waves add together positively. So let's say we had a wave that looked like this. Let's see how I want to do this. Just like that, okay? And it's traveling in this direction. And let's take another wave over here. Okay. And let's have it, oops. Erase that real quick. And it would be traveling, gosh, sorry. That in that direction. And then these two waves are going to overlap the central point. So let's move them ahead in time. So if we take this blue one, let's put it together, and then we'll group it and clone it. We'll do the same with this. We got to put this together. So let's do it 80 times. Group it. And clone it. So now, actually we'll put these on the same plate, just coming right at each other. Same place, so that they'll match right up. Okay, so then after, I must have group. So here they are coming towards each other. And now though, instead of being right here, they've moved forward in time. We'll move it up one. We'll take this one move it, instead of here, up one like that, so we can see they're getting closer together. We go to another instant in time and move them they're even getting closer together. So now we'll move it up like that, and then move this one towards that as well, almost ready to overlap. They come towards each other. Okay, they're going to start overlapping soon. Okay, now we have some overlap. So, in this first part of the wave over here, the blue part right there, whoops, there was no, why does it do that? I don't know. Well, there was no overlap on that, in that part. And over here, same thing, there's no overlap there. No overlap there and over here. Okay, so, whoops. But we can see that in this part we do. So if we took like a point right here, we would have 1, and it would be added to a little less than, if the blue line was 1 and the red line was 2 there, it would be 1 plus like 1.8, which gives you like 2.8. So the line goes up to like that there. And in this point right here, they're both like 1.5 plus 1.5, which gives you up to 3 when they add together. And then here the green is like 1.8 and the blue is like 1, so that gives you like 2.8 again. And so when they add together that region, you would get something like that. Okay? So the wave, when both go together, will add and increase the amplitude in that region of overlap. Let's continue on with it. So now we move forward again with the blue one, and again with the green one. How much? So the blue, we'll just move it to like a half step to where they exactly overlap. At that point, if you took a point like right here, you could see it's like 1 plus 1, that would be up at 2. This would be like 1.7 plus 1.7, like 3.4. Be like there. This is 2 plus 2, it's 4. And the same on the other side. So you get this overlap wave like that. And now, and then afterwards, the green wave will move on past it, and the blue wave, it will move on past that one. So they'll move through each other. It's just where they overlap that you have the interference. And the same thing works destructively as well. So let's look at a continuous wave now. So something, say, like this. Oh, let's see. So let's say we had, we'll just put this on here like that so we can see the midline of the wave. If we had one wave that looked like this, there's the continuous wave, okay? And then underneath that, we added it to another wave that looked like in the same wave, really, except, two different disturbances. Well, those constructively interfere, so when you add them together, those two together, you would get something that just added together as well, so that in each region, like this point is -2, and this, or, okay, so this is like -2 here, and that's like -2 there, and that would give us -4 down below. So at that point, we'd be down at -4. 0 plus 0 is 0 at this point here and there. And then we have 2 plus 2, which is 4. So we'd go up to 4. And we have 0 again, and then -4, and then 0, and then 4, and then 0, and then -4, then 0, then 4, and then, oopsies, come on, I got off track here. Move this over slightly. That should be there. There's that. Oh, come on. And shift it over one. Let me just erase all these. Okay, and then up at 4. But you see, it's just adding the displacements together. That's the important part here. Okay, so that the added wave would look something the same frequency, the same wavelength, the same speed, just different amplitudes of the black plus the green gives the red. Destructively, the continuous wave, you could take one where we took this wave here, hold this whole thing, okay. If we took this wave there, and then another wave, this one we're going to flip, okay? So that they're really exactly out of phase with each other. This one goes down, when this one goes up, and vice versa. That means when they add together, well, at every place, the minus is canceled by the plus. The minus is canceled by the plus, or the plus is canceled by the minus. So you get 0 is the overall sum of those two waves like that. And that's called destructive interference. When the waves destructively interfere, they reduce amplitude. When they constructively interfere, like up here, they increase amplitude. Now, sometimes you could take waves that are slightly out of phase with each other, okay? And when you do that, you can get a phenomenon like this on this chart. The blue and the red are slightly off, okay? One has a frequency, let's say, of 0.02, and the other one has one of 0.022 over here, okay? And when they add together, you get a frequency that's green. The green is an interference where you have this high area and this low area and high area, low area, high of a much smaller frequency. So instead of being like 440, 442, let's say, of the blue and the green, you get a frequency that is lower. Then you also have the other wave below it that looks like that. So this ends up giving you this beat phenomenon. I'll play a little bit now, although we'll do it in class, so you probably hear it much better. We could do the frequency generator and stuff too. So this will be 256, and I don't know, slightly off of 256. Okay, so put the microphone in front of them. Maybe you heard there up and down of the beat frequency. We heard the frequency, the 256, let's say the 258, but there's also this other one going woo, woo, where the sound got louder and then softer. So in the beat frequency, occurs when two similar frequencies are played, so to speak, together and in places, and well, we'll just say and interfere with each other, producing a beat. And the beat is equal, the frequency of the beat is equal to the frequency of one wave minus the frequency of the other wave, absolute value. So if you had a one frequency of one, let's say one frequency was 202 hertz and the other frequency was 200 hertz, then your beat frequency is simply 2 hertz, which is 2 beats per second. So something like that would be the beat that you would hear. Okay, and then the third type in here that we'll talk about is something called resonance. And we'll really look at this more in a lab that we do, and I'll show you a video on the Tacoma Narrows Bridge. But this has to do, and we use the Slinkies too to look at it, with wave interference with a reflected wave. With the generated and reflected wave. Okay, so if an opera singer sings a high-pitched note that matches the natural frequency of a vibrating cup, so her voice will actually go and begin to vibrate the sides of a glass, wine glass, okay? And as it vibrates it in such a way that the sound that's in it reflects off of it, and that reflected sound adds to the generated sound. It adds to the vibrations of the walls of the cup, and eventually the vibration is too great, and it shatters the glass. And so we call that it's matching its natural frequency of the glass. We have to design buildings that cancel out frequencies or destructively interfere, not constructively interfere. so that if the wind happened to match the natural frequency of a building and it kept adding, the building would sway slightly in the wind and then start swaying back and forth. And if it matched the wind coming in, it would actually just more and more resonate until the building collapsed. So they designed those to cancel each other out so that the building won't blow to the point of collapse or move to the point of collapse. Bridges are the same sort of way. So we don't want the motion that's being generated to match the reflected part coming back. Ears work through resonance. When sound is produced by vibrations in a person's, say in a person's voice box, that travels through and then gets to our ear, but our ear resonates that sound. And that resonance of that sound produces enough that we can hear it. And that works in the range 20 hertz to about 20,000 hertz. Okay. So it's the ability to reproduce oscillations. Oops. The ability to reproduce oscillations in sympathetic mediums. So the oscillations have to match. They have to have the natural resonance of the produced vibration that's occurring. Microwave ovens provide a great example of resonance with light. They create waves that resonate with a wavelength of about 12 centimeters. And that happens to be also the natural frequency of water molecules. So the water molecules, because of the microwaves that come in, they shake. But when they shake, each time the reflection of them adds to the generated microwave, and it builds up and they shake more and more and more. And that shaking produces thermal energy, and rubbing together the particles, or friction, and heats up the material, or the food. So really, we're cooking our food through microwaves, resonance, and friction. And that's it for topic 7.2.